Morning, everyone. Morning, everyone.
Just a rhyme without a reason. Never breaking things. Keep the number six. Now your life without a season. I will occupy. I will help you die. I will run through you. Now I will you too. Obey your master. Your life burns obey your master. Testing your mind, testing your dreams. Just know my name is on your screen. Master, master. Just know my name is on your screen. Master, master.
Morning, everyone. Master of Puppets is, in my opinion, the best album, best Metallica album. How are we doing? Questions while we wait another minute or two till people come in? Morning, everyone. How are we doing? I thought we'd wake ourselves up on this rainy Monday. You can expect copyright claims, right? Jack is saying there's a question about rational and irrational, correct? Indeed there is. You know what that means, right? Yep, it's fine. So, yeah. So perhaps we should define rationals versus irrationals, right? Rationals rational numbers denoted by Q are real numbers whose decimal expansion either terminates or repeats, versus irrational numbers usually denoted like this, or sometimes cubo, sometimes just like that, is everything else. Lucas, I don't have the book with me. You'll have to tell me what that Question is, so as Jack suggests, square root of a negative number would not be irrational. Square root of a negative number would be a complex number. But square root of 2 is irrational. Pi is irrational. E is irrational. There are a lot more irrational numbers than there are rationals. Consider this. What is happening? So first of all, you know the exponential function is continuous, right? So limit of the exponential is just the exponential of the limit. In other words, you can bring the limit inside by continuity of the exponential function. So the real question is, what is happening to secant as you go towards pi over 2 from the right? Eddie is asking, aren't rational and irrationals both infinite sets? They are. They are. And it's a very nice question to ask. Can we talk about sizes of irrational sets? Because I said there were a lot more irrational numbers than there were rational numbers. How do you compare two infinite sets? How can you say one infinite set is larger than the other? It's a very, very nice question. And you'll find the answer in Math 180. So secant x, what is happening to that? Well, secant is 1 over cosine. So the real question is, what is happening to cosine? Well, you know the graph of cosine. And here exactly is pi over 2. So you know problems are occurring at pi over 2. At pi over 2, cosine is 0. So you have 1 over 0, you have some sort of infinity. We need to determine if it's positive or negative, but if you're taking numbers bigger than pi over 2, cosine is going to be negative, so the numerator is positive, the whole thing is negative. Negative infinity is the answer. And as this gets closer and closer to negative infinity, right, gets larger and larger negative number, e to a large negative number is going to be, you know the behavior of e as it approaches negative infinity. Right, you know the graph. This is going to be 0. Absolutely. Page 67. No, page 139. Number 67. Lucas is asking for. You have the following inequality. You had some function sandwiched between these two things. And we were asked to find why isn't limit pi over 2 approaching 0? Well, it's the limit of secant. Secant is 1 over cos. And cosine is approaching 0, but not secant. Secant is 1 over cos. So you have f satisfying this inequality, and the question is asking, what is the limit as x goes to infinity? Right, that's the question. And I'm sure you've noticed already. You think minus 1 is inside the square root, fine. Could be. Doesn't really matter. Inside or out, it's going to be the same answer. Squeeze theorem is the idea. So the 1 over infinity, we don't have 1 over infinity. We have 1 over 0. 1 over 0, which gives us negative infinity in this case, because you're approaching pi over 2 from the right. And so this goes to negative infinity, and e to the negative infinity is 0. 5 is the answer, absolutely right, because the limit as x goes to infinity of 10 e to the x minus 21 over 2 e to the x, this has the form infinity over infinity, an indeterminate form, so you know something's got to be done. What are we going to do? We're going to factor out an e to the x from the numerator. Which will conveniently cancel with the e to the x in the denominator. And as x goes to infinity, e to the x goes to infinity. So this is 21 over infinity, which is 0. So this is 10 over 2, which is 5. Similarly, on the other side, limit as x goes to infinity of 5 root x over root of x minus 1 will factor out, well, so again, if you blindly plug in, you get infinity over infinity again, right, an indeterminate form, so you know something's got to be done. We'll factor out an x from the square root. And now square root of a product is the product of the square roots, the usual. So 5 root x, and then root x times root 1 minus 1 over x. These cancel out again, and as x goes to infinity, 1 over x goes to 0, so we're left with 5. So this thing goes to 5, this goes to 5, and consequently the stuff in the middle goes to 5 by the squeeze theorem. There it is. How are there only 80 people here? I'm starting to worry that people aren't taking this course seriously. Is it going too slowly? Is that the issue? Am I boring people? Yeah, exactly. I mean, it's a 78, 80. Yeah, well, exactly. I mean, sure they have 500 views, but I mean, people really should be attending. All right. I mean, it is troublingly low, I feel. Anyways, All right, so what are we doing? Let's go back to, right? I mean, there's nothing like watching it live. Exactly. You know, you can ask questions and stop me. What I'm afraid of is that people put off the lectures and watch them all in a bunch, and then don't do the work. Anyways. Let's go back to what gave rise to the study of limits, right? The idea was this: we were importing the idea of a tangent line to a function. At some value x. And what we suggested was, well, if you look at x plus h, look at the image, right? So this is your function at x plus h, or this is the point x plus h, f of x plus h. And whereas this was the point x, f of x, and we said, why don't we look at the line joining these two things, or rather the slope of that line, right? Because if you're looking for a tangent line, as long as you have the slope, since you already have the point, that's all you need. So let's calculate the slope of this line joining the 2 points, which is the change in y divided by the change in x, right? So this minus that. Over this minus that. And we have this, and our idea was to observe what happens as the h is getting smaller and smaller, closer and closer to 0, right? If you take the h smaller and smaller, you get a better and better approximation, and you see how the line joining the 2 points is getting closer and closer to the actual tangent line. So we said we were going to investigate the behavior of this as h goes to 0. So how does this behave? And that led us to the idea of limits, right? We were going to describe how this behaves as h goes to 0. But before we tackle this, we had to understand the idea of limits. And now that we have mastered the limit concept, now we're ready to study this. So, definition. Given a function, or we say, given a function, f of x, and a point in the domain, we define the derivative of f at a denoted f prime of a to be the limit as h goes to 0 of f of a plus h minus f of a over h. Right? Exactly this definition. No date on the midterm yet, but we'll announce something by the end of the week. So on Friday, I'll let you know when the midterm is. We'll decide. Right, so here we've defined the derivative of f at x equals a, denoted f prime of a to be this. This is the derivative. Or, what is this equation used for, right? Well, so from here, right, from this idea, f prime of a is the slope of the tangent line. At x equals a. Right, so immediately there will be no epsilon delta questions on the midterm. Right, so f prime of a is this. This is the slope of the tangent line at x equals a. Or, if you prefer, f prime of x, right, and you just replace a with x, and you get the limit we were looking at originally, which is really a rule or a function which gives you the slope of the tangent line at every point x. Let's illustrate with a few examples. Let's find the derivative if f of x is x squared plus 3x minus 4. Jonas is asking an excellent question. If the whole function is over h, where h goes to 0, won't this limit necessarily be some kind of infinity? And it's an excellent question. So first of all, I should say we define this if it exists. Right, so if the limit exists, it's not immediately clear that the limit does exist. It might not exist in every case. And as Jonas suggests, the denominator goes to 0. And it's a beautiful observation that in order for this limit to exist, the numerator better go to 0 as well. Right? You better have a 0 over 0. Otherwise, you're going to get some sort of infinity. Let's do a few examples first, though, and we'll come back to that nice observation. So, as Pamela suggests, we're now taking knowledge of the limits that we've studied for the past few weeks, and it's going to help us to solve for the derivative. So we're looking for f prime of x, and by definition, f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So let's evaluate this. What is that? Everywhere you see an x in your function, you're replaced with x plus h. So this is x squared plus 3x minus 4. So that's your f of x plus h. Minus f of x, which is the original thing, all over h. Well, I know a lot of you have seen the derivative before, and you know what's coming up. So the obvious question is, can we use some derivative rules? The answer, of course, is no. I don't know any derivative rules. We have just defined the derivative to be this. This is what we need to use. There's no saying 2x plus 3 directly. We have just defined the derivative to be this. This is the only tool we have for now. So let's evaluate this. This is what we need to evaluate. Let's expand and simplify. Exactly, right? Who even knows what derivative rules are? Nobody knows. Now, seriously though, for those of you in the know, this is of tremendous importance. This is the definition of the derivative. And you can expect questions on the midterm and even on the final that ask you to find the derivative using the definition. This is what needs to be done. That's it. Also, more importantly, if you invent a function, right, in your work outside of this class, you come up with a new function. One of the first questions that should pop up in your mind is, what is the derivative of this new function? And if it's a function nobody has ever seen before, then you know what the derivative is, and so you have to evaluate this limit. Jack is asking if infinity times 0 is equal to 0, and you know, we saw last time, infinity times 0 is an indeterminate form. So let's expand this. Square the x plus h, that's x squared, plus 2xh plus h squared. Distribute the 3. All over h. So Jack, you should have a few of these examples readily available to you immediately as to why infinity times 0 is not 0. Infinity times 0, in this case, is 1. And then 4, 47, and so on and so on. Observe that the x squares cancel out nicely. The 3x's cancel out. And the 4's. What does that leave us with? Let's just rewrite what's left. 2xh plus h squared plus 3h. I think that's it. all over h. And now if you plug in h equal to 0, well, now you have a 0 over 0. We have a 0 over 0. Something needs to be done. You know 0 over 0 is an indeterminate form, right? That's why we were studying limits before. But now that you've mastered limits, factor out the h, very nice. The h's cancel out nicely, and as h goes to 0, this goes to 0, so the whole thing is 2x plus 3, as suggested by a few people, but this work needs to be done. So it's always nice if you know what the answer is going to be, but I still need to see that work. How are we doing? Let's try another one. I will not teach you the short method today, Con, but we will learn on Wednesday. Of course, you can confirm your answer by differentiating. Absolutely. Will we have to explain the limit formula? No. I mean, it's nice to understand what's happening, but I will not ask you to explain it. So you can simply use, I mean, you know, we called it a definition, right? F prime is the limit as h goes to 0 of f of x plus h minus f of x over h. I mean, I certainly would like you to understand geometrically what's happening. It's not that difficult, right? And it certainly motivates the whole idea of the derivative. So 2x plus 3, Jasmine, is the final answer. So again, we're looking for the derivative of this function. So everywhere you see an x in your function, you replace with x plus h minus the original function over h. And as h goes to 0, this goes to root x minus root x is 0. You have a 0 over 0. An indeterminate form. And you know, I mean, just go back to this. When h is 0, you get f of x minus f of x, which is 0 over 0. So it's always 0 over 0, right? Conjugate, I say always, but it's almost always. So conjugate, very nice. Let's multiply by 1, namely root of x plus h plus root of x over itself. Absolutely. You're multiplying by 1, you're not changing anything, right? This is a very nice trick that we learned when we were evaluating limits. So what is h meant to represent? Let's finish up this question and I'll answer. You know, I say Jasmine because it's from the French, but I mean, it could be Jasmine. Who knows? Let's finish that up and then I'll answer Jasmine's question. Multiply everything, and you know what's going to happen when you multiply the numerators together, right? It's a minus b times a plus b. So it's just this squared minus this squared. Con, don't let that faze you. Don't let that faze you. They have seen it before, and there are shortcuts, which we will discuss later. But right now, it's the process that's important. So if you multiply this out, what do you get? I claim the numerator becomes x plus h. Indeed they are. I claim the numerator becomes x plus h minus x, and the denominator will leave factored Is everybody comfortable with the numerator being that? We do FOIL, right? This times this gives you the x plus h, and then this times this, so root x times root x plus h, and then minus root x times root x plus h. So they cancel here. You see that, Tom? The middle terms cancel, and then you get a minus x. Is that clear, everyone? Again, it's the process that's important here. It's not the actual answer. The x's cancel, leaving you with just an h in the numerator. And then the h's cancel, leaving you with a 1 over. One over this. Now we've gotten rid of the issue, namely the 0 over 0. We no longer have a 0 over 0. As h goes to 0, this goes to 0. So we're left with 1 over root x plus root x, or 1 over 2 root x. Again, for those of you who know the shortcuts and were able to come up with that just by looking, that's great. Nothing wrong with that. Except if I ask you to find the derivative using the definition, this is what needs to be done. So this is a very important process. It's what gives rise to the whole course, really, right? It's what motivated our study of limits. And sometimes you have to resort back to this definition. Is this method called first principles? You can call it that, for certainly. On an exam, I would say find the derivative using the definition. Jack is asking, why is it 2 root x in the denominator here? When h goes to 0, that disappears, and you get root x plus root x, 2 root x. Well, so somebody's not sure what this is trying to tell us, and Jasmine had the same question. So let's go back to that picture that we were looking at in the beginning, where I suggested we were going to try, well, first of all, import the idea of tangent line from the tangent of a circle, right? If you have a circle, not the best circle, but if you have a circle and we say a line is tangent to the circle if it just touches the circle at one point. Here, we want to do the same thing locally to a function. So we're looking for this line. This line going through the point x, f of x, right? Or, well, let's call it a, if you prefer. So I'm looking for the tangent line at the point A. And since we already have the point, all we need is the slope. So as David suggests, all we need is the slope, and this gives us the slope. Let's understand why that is. What we said we were going to do is, we were going to look at a plus h, where h is some value, doesn't matter, right? In other words, just take another point on the graph and look at the line joining the two. This, sometimes referred to as the secant line, this line is going to be an approximation to that one. Terrible approximation, indeed. But let's just go with it. This point is the point a plus h, f of a plus h. And the slope of the line joining these 2 points is the change in y divided by the change in x, or this minus that, over this minus that, a plus h minus a, or if you prefer, f of a plus h minus f of a over h. And while this is a terrible approximation, as h is getting smaller and smaller, the approximation, right? This is your new a plus h, and then another a plus h, right? As h is getting smaller and smaller, closer and closer to 0, you see that these lines are getting better and better, closer and closer to the actual thing. So we're going to investigate the behavior of this slope. We're going to investigate the behavior of this as h goes to 0. That's what we have. That's what we're doing. So this thing, this limit here, gives us the slope of the tangent line at any point x. And Andrew is asking, what is the significance of the tangent line? Well, this tangent line, this rule for the tangent line, right, this slope of the tangent line has many, many applications that we're going to study throughout this course. A quick answer is in conversation. right? You've heard the term going off on a tangent. And that's exactly what the tangent line does, right? If you think of conversation as being fluid, but then suddenly, if you're going off on a tangent, you keep talking about, well, yeah, so that's a very nice idea. But concretely what? What is this tangent? What is that? Well, this is the slope of the tangent line. What does it do? Suppose, so first of all, observe that it's the rate of change of y divided by the rate of change of x, right? So if you're viewing the curve as locally a straight line, we're asking the question, what is the slope of this line, or what is the instantaneous rate of change? Right? So the derivative is sometimes referred to as the instantaneous rate of change. It tells you how fast something is changing at that particular moment. In particular, if you have a function that describes the position of a person, a car, a particle, the rate of change, how fast the position is changing. Think of yourself in a car, how fast you're moving from one place to the other. Well, that's the velocity. The derivative is the velocity. How fast the velocity changes? Right? You're in a speeding car and you floor it. How fast the velocity changes? Well, you know that to be the acceleration. So somebody's asking, why is the slope not always a linear function? Well, the tangent line is a line, so it's always linear, but the slope itself, the slope may change very much. So there's no reason for the slope to always be linear. And I mean, we have one nice example. Our second example here, the square root function, had a slope which was very different. Let's take another example. We're still looking for the derivative using the definition. So Jake is asking, can we measure the tangent line anywhere in the curve? Pretty much, as long as the limit exists, then yes. The derivative is the slope of the tangent line at any given point. Yes. Assuming the limit exists. So same thing here. We're looking for the derivative. Right, and that's the definition. This is what we need to evaluate. Go ahead and replace the numerator by what it is according to this function. So everywhere you see an x in your function, you replace with x plus h. This is 1 over x plus h minus 1 over x all over h. And as h goes to 0, You get 1 over x minus 1 over x, so that's 0 over 0. An indeterminate form, something's got to be done. You tell me, what are we going to do? Again, it's good that you know the answer, but now it would also be nice if we knew how to evaluate this. What are we going to do? You tell me. Common denominator. Common denominator sounds like a plan. Let's do it. See what happens. What is a common denominator? You know what it is. Common denominator for the numerator is going to be the product. Right? Product. And so we get x minus x plus h. Is that right? Everybody with us? Common denominator for the numerator. Blah, blah, blah. There we have it. Very nice. Now, let me ask you, where does this h go? Does it go in the bottom or back on top? Can we rewrite this as one single fraction where the h either goes on top or on the bottom? Where is it? Top or bottom? Everyone? Bottom it is, right? Absolutely, thank you. The x's cancel. That's nice. The h's cancel, getting rid of the 0 over 0. Isn't it a minus h? First of all, yes, thank you, thank you, thank you. It is a minus h. It is a minus h. Do I want to cancel these? Leaving us with a negative 1. Thank you. Nice catch. So negative 1 on top. X times x plus h. Thank you, everyone. Absolutely. Very nice catch. And as h goes to 0, what is the limit? Will the points be taking off if we do not plug in h to show there's an indeterminate form? No. I mean, if you do all of this work without writing this, that's fine. That's fine. It would be understood that you knew. And that would be fine. So here it is. The derivative of 1 over x is negative 1 over x squared. What does this represent? Right? 1 over x, you know the graph of that. Let's just look at it in the positive part. And if you chose any point, A, the slope of the tangent line would be negative 1 over a squared. The derivative gives you a rule, a function, that allows you to evaluate the slope of the tangent. How did you get the numerator? So this is our definition. This is the definition of the derivative. So f of x plus h minus f of x. F of x is this. So it's the 1 over x. The real question is, what is f of x plus h? Everywhere you see an x in your function, you replace with x plus h. So that's how we get this numerator. And then you're subtracting two fractions. So common denominator. The common denominator is going to be the product. So here I need an x. I'm going to multiply by x over x. I'm multiply by 1. I'm not changing anything. And here I'm going to multiply by x plus h over x plus h. I'm multiplying by 1. I'm not changing anything. So you get x minus x plus h over the denominator. Well, I mean, what does the tangent line represent? It essentially tells you that if you were moving along in this direction, right at this point, the rate of change would have been negative 1 over x, 1 over a squared. So if you kept going on a tangent, that's the slope it would have been. How would this work for lawn? Exactly, right? Imagine those first people, Newton and company, defining this idea of derivative and then applying it. I mean, in the case 1 over x, it's fairly simple. In the case of root x, relatively easy. We did a polynomial x squared plus 3x minus 4. Worked out nicely. But now what about ln? What about exponentials? What about sine and cos? These are all excellent questions which took years and years and years of work to work out. Let's do a few questions from the book. Maybe one question. And isn't it satisfying to understand why we do calculus? Right? Why we need to understand limits in order to understand how this thing behaves. Right? So we first study limits to understand how limits work, and then we apply limits to this expression. It's very nice. It's very nice how everything comes together. And then, like I said, I mean, the obvious question somebody was asking, Thomas up there, was asking, what about ln? Right? And imagine hundreds of years ago asking that very question. What about ln? How do I evaluate? How do I evaluate ln of x plus h minus ln of x over h? How do I evaluate this limit? I mean, of course, it's much, much, much better than just throwing out these derivative rules. And that's the problem with mathematics education in high school, where you're just thrown out these formulas. I mean, that's not what math is. Math isn't formulas. Math is understanding. Well, Jasmine is absolutely right? This limit as h goes to 0, since you have knowledge about limits, it's really a limit from the left and limit from the right. So this limit exists if and only if limit from the left and limit from the right both exist and are equal. In these examples, we can evaluate both limits simultaneously because it's going to be the same thing. But in some instances, you might have to break it up into a limit from the left and limit from the right. So let's finish that up. Everywhere you see an x in your function, you replace with x plus h. What do we have? Minus the original function. All over h. Once again, right now we're assuming both limits exist. Well, I mean, we're doing a bit more than that because now you have experience with limits. And you know you don't always have to break it up into left and right-handed limits, especially when you know it's going to be the same work. And that's exactly what would occur here, right? Whether it's plus or minus, there's no difference in the work you're going to do. So there's no reason to split it up into two pieces. But as you know, sometimes there is need to do that, but not in this case. What are we going to do? I think common denominator, right? Common denominator, which is x plus h plus 2 times x plus 2. The whole thing over h again. And we're going to have an x plus h times x plus 2 minus x times x plus h plus 2. The whole thing over h. And this h is going to go back to the bottom as we saw in the previous example. Let's FOIL this, right? Distribute x squared, hx, 2x, and 2h, and distribute the minus x squared minus xh minus 2x. The x squares cancel. The xh's cancel. The 2x cancel, leaving us with 2h over h, x plus h plus 2, and x plus 2. The h's cancel nicely, thus getting rid of the 0 over 0 business. Can we rewrite this to make the calculation easier? Absolutely, we can do that. Very nice. And as h goes to 0, this goes to 0, so we are left with 2 over x plus 2 all squared. Very nice. Very nice. How are we doing? Questions? Anyone? No, factored is easier. Leave it factored. Factored is easier. Thank you all for coming, folks. Practice this. We're doing stuff on page 163. We'll pick this up again on Wednesday. No. The midterm will be late October. There's no need to throw it in right after Thanksgiving. The final may be a mix of multiple choice and long answer. It'll depend if it's in person or online. Of course, online, there's really no point in having multiple choice questions. Do we have to state restrictions for the domain? We usually relax that. It's a good habit. It's a good habit to do, right? You don't want x to be -2 here. So if you're in the habit of doing that, please continue. I don't always do it, but who knows on the midterm? We'll announce this on Friday. We'll announce everything you need to know about the midterm on Friday. No, not everything you need to know, because we'll make an announcement on Friday with respect to the midterm. Thank you all for coming, folks. You guys have a good rest of the day, and I will see you on Wednesday. Yeah, look out for an announcement, Jasmine, on Friday. Does the h from the denominator in the upper right equation just move above to the next denominator? It does, right? Right, this h goes in here exactly like we did in the previous question. The idea is this: if you have a over b over c, that is a over b divided by c. And when you divide by a number, it's like multiplying by the reciprocal. So that's why the c goes in the denominator. All right. You guys have a good one. See you on Wednesday. Thank you all for coming.